Hi guys, it's Dr. Bay and here's Bugsy, and today we're going to go over Wittig and Baeyer Villiger oxidation reactions, so stay tuned.
Organic chemistry,
Taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy, soaring through the sky, triumphantly we fly, give rise to the complexity of life, living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
The final type of carbonyl nucleophile that could attack the electrophilic center of an aldehyde or ketone is phosphorus-based. The Wittig reaction converts a ketone or aldehyde into an alkene by forming a new carbon-carbon double bond at the location of the carbonyl group. Because it forms an alkene product, this reaction is also known as the Wittig olefination reaction, where the term olefin also means an alkene. The Wittig reagent is a phosphorus ylide, which is a carbanion that's stabilized by resonance. An ylide contains a negatively charged atom, C- in this case, that is directly attached to a positively charged heteroatom, P positive in this case. The mechanism of a Wittig reaction starts with a 2+2 cycloaddition, where the nucleophilic C- in the Wittig reagent attacks the electrophilic carbon of the carbonyl. Then the carbonyl pi bond attacks the positively charged phosphorus atom to form a four-membered ring intermediate called a oxophosphatane. Then this intermediate undergoes fragmentation where the phosphorus-carbon bond breaks to form a new alkene pi bond, while the CO bond breaks to form a new pi bond between O and P. This gives the alkene product. In general, Wittig reactions produce the Z-alkene, where the two largest substituents on each side of the alkene are cis to one another or pointing in the same direction to form a Z-alkene. In this example, the following aldehyde is reacting with a Wittig reagent. In the product, notice that the methyl group and the phenyl group are pointing in the same direction, which in this case is pointing to the left, in order to form a Z-alkene product. However, if the Wittig reagent contains an electron withdrawing group or phenyl ring, which is also called a stabilized Wittig reagent, then the E-alkene is the major product. This is because an electron withdrawing group or phenyl ring can stabilize the anion of a Wittig reagent due to resonance. In this next example, notice that the Wittig reagent contains an ester group, which is an electron withdrawing group. This means that the major product should be an E-alkene where the two largest substituents, phenyl and ester, are pointing in different directions or trans to one another. In this next example, the Wittig reagent contains a phenyl ring, so the major product should also be an E-alkene where both phenyl rings are trans to one another by pointing in opposite directions to form an E-alkene product. Now let's take a look at another new reaction. The Baeyer Villiger oxidation converts an aldehyde or ketone into an ester via an insertion of an oxygen atom using a peroxy acid. The mechanism starts with one of the lone pairs on the peroxy acid acting as a nucleophile and attacks the electrophilic center of the carbonyl. Then an intramolecular proton transfer occurs to form the following intermediate. Then one of the lone pairs in O- comes back down to reform the carbonyl simultaneously while an alkyl group migrates to the other side of the oxygen atom. Meanwhile, the oxygen-oxygen bond breaks to form a new carbonyl and the CO pi bond breaks to form a new lone pair on oxygen. This produces two products, the desired ester molecule as well as a carboxylic acid side product. Now, when an unsymmetrical ketone reacts with a peroxy acid, formation of the ester is regioselective and is dependent on what substituents are attached to each side of the carbonyl. Substituents are ranked in terms of speed of migration, which also can be called migratory aptitude, as shown here. Hydrogen atoms move the fastest and methyl groups move the slowest, so you want to make sure you move whatever substituent is fastest. In this example, let's first determine what substituents are attached to the carbonyl. To the left of the carbonyl, highlighted in blue, is an isopropyl group, and to the right is a methyl group. Isopropyl groups are considered to be secondary, which means it will migrate faster than a methyl group. So the Baeyer Villiger oxidation product will insert the oxygen atom in between the carbonyl and the isopropyl group. Now in the last example, to the left of the carbonyl is a phenyl ring, and to the right is a hydrogen atom. Hydrogen will migrate faster than phenyl, so oxygen from the peroxy acid will insert in between the carbonyl and the hydrogen atom to eventually form a carboxylic acid product. So in summary, we learned two new reactions that involve carbonyls. The Wittig reaction converts a ketone or aldehyde into an alkene by forming a new carbon-carbon double bond at the location of the carbonyl using a phosphorus ylide reagent. And the Baeyer Villiger oxidation converts an aldehyde or ketone into an ester via an insertion of an oxygen atom using a peroxy acid reagent.
Organic.